Hi, everyone. So in this video, I just want to look at Kruskal's algorithm of finding the minimal spanning tree of a weighted network, or maybe using our other knowledge of how we can find all spanning trees and using another clever approach. So why don't I start out with Kruskal's algorithm in this particular case? Um, so I'm going to copy this because we'll use another method in a moment. I'm just going to look at this one example, but yeah, we'll see how well it works. All right, so Kruskal's algorithm tells us that we should look for the cheapest link, our cheapest edge, and we should add it. And we should keep on doing so unless we create a circuit. And then if we were to create a circuit, we just don't include that and move on to the next cheapest. So let's see. Um, I'll go ahead and just say, all right, I'll actually draw over the edges and when I need to. So there's an edge here. The one is the smallest number uh, of all of the weights. Two is the smallest number, the next smallest. I'm not making any circuit with three. Four is disconnected, so I'm happy with that. Five is here, also not making a circuit. Six, I've got over here. Seven is up here. Eight here. Nine is over here. 10 here. And now, if I were to make 11, I would make this circuit. So I don't want to add 11. I move on. I move on to the next guy. And now 12 is the next one. But again, if I have 12, then I have this circuit, so I don't want 12. So finally, I move on and I just add at 13 here. Okay. So this is Kruskal's algorithm is allowed us to do this. Did it very quickly, very efficiently, and gives us the minimal spanning tree. So this red guy, this is the minimal spanning tree for this graph, for this network. And I won't add up the total weight for this spanning tree, but it's not hard to do. And I just wanted to point out in this short video that you could have approached this problem, not all problems. I mean, Kruskal's algorithm is certainly pretty good, pretty quick, and I'd recommend it in all situations. But there's another way you could have approached this problem for this particular graph, and that is by the sort of brute force where we enumerated all of the different spanning trees. And you'll recall how that works. We found sort of, in this case, we have these two disjoint, in other words, non-overlapping circuits, one here and one here. And we knew that if we wanted any spanning tree for this graph, the way that we could get any single spanning tree, any possible spanning tree, was to eliminate an edge from one circuit and another edge from the other. So in other words, we eliminate two edges. Once we've eliminated two edges, we have um, a spanning tree. So, however, what happens when we eliminate an edge from a spanning tree or from a graph if we're counting the total weight? Well, what happens is we decrease the total weight of the graph by the weight of that edge that we're eliminating. So if we want to get a minimal spanning tree, one with the smallest total weight, the way you can do that is you can look in each of these circuits and say, I'm going to eliminate the largest weight, the edge with the largest weight. That's the one I'm going to choose. And similarly, over here, you can say, well, I'm going to eliminate the edge with the largest weight over here. And if you do that, what happens? Well, the largest weight is 11, and the largest weight here is 12. And now you'll see that what you're left with is precisely what you got with the Kruskal's algorithm. You get the same exact spanning tree. And so in some sense, this is brute force, but it's not that hard because we know uh, in this particular case for this kind of a graph exactly how to find all spanning trees. So it's sort of clever brute force. Uh, Generally speaking, though, again, if you have a high redundancy, a large redundancy, or you have a complicated graph, Kruskal's algorithm is far preferable. All right.